Liu and Shuchen Zhu. And they're going to tell us about early fault-tolerant block encoding with low Clifford+T count for second quantized Hamiltonians. Yes, we have to wait.
I'm seeing the chart, but their charts are not up.
One sec. Which folder? Okay, I don't know what's going on. Do you know how this works? Yeah, the mic is out there, but I don't know how this thing works. Do you know how to?
We end early?
No. It was a 20-minute talk. Okay.
Hello, everyone. Thanks for coming to the talk. I'm Shuchen, this is Diyi. We are presenting block encoding with low gate count for second quantized Hamiltonians. And this is a joint work with Lin from Berkeley, Guanghao from Google, and Chao from Berkeley Lab. The archive version will be online very soon. Sorry. It's this one. Sorry. Okay. We all know it's very hard to understand and predict the behavior of quantum many-body systems. Many interesting quantum phenomena involves interactions between many particles, and it is classically hard to compute as the computational complexity grows exponentially with the system size. And the quantum algorithm can help better understand these important problems. And many quantum algorithms start with a matrix as input. For example, simulating quantum dynamics, computing the spectral properties, or solving system of linear equations. And for input, we use block encoding, which is the technique for embedding a scaled non-unitary matrix inside a larger unitary matrix. So with these techniques, we can have access to a wider range of matrix using quantum algorithms. More formally, given a matrix A, if we can find a scaling factor alpha, a precision epsilon, and a unitary matrix UA, such that this inequality holds, then we say this UA is a alpha M epsilon block encoding of matrix A. And on circuits-wise, it is implemented through two important oracles, OA and OC. So we call OA oracle the amplitude oracle. So on high level, it stores the non-zero matrix value of A. And we call OC the sparsity oracle, and it stores the non-zero index of matrix A. And when you put OA, OC in this way, you obtain the unitary UA, which is a block encoding of A. And you may have asked, looks different from the traditional LCU method where a prepare and the select oracles is used. So here's the reason. So we study this set of implementation because on the surface level, it looks very hard to implement. And to the best of our knowledge, the prior work only study it up to its query complexity level. And so in this work, we open the black box of OA and OC and try to study the practicality of this type of implementation by studying the complexity to the gate level. And here's a summary of our result. So we study the block encoding of second quantized Hamiltonian. And for general Hamiltonian, we have a quadratic improved T-gate count from n to the 4 to n to the 2. And for translational invariant Hamiltonian, we have an improvement with the precision, and that's a quadratic improvement. And for the localized Hamiltonian, we have a T-gate count improved from T to the 4 to T. And the core of the improvement relies on the usage of select swap circuit, which is essentially a quantum lookup table that allows superposition of classical data. And it was first proposed by Guanghao, Vadim, Luke Schiffer, and published in Quantum 2024. So on the high level, it has two parts of circuits. One is called select, and one is swap. So the select part of the circuit corresponds to some high address bits, and it divides the data into different groups. And only one group will be activated by the select. And then the swap circuits take over, swap out the data stored in the location corresponding to the lower address bits. And the cool part of this structure is that there's a tuning parameter lambda that you can choose to set the relative size between select and swap to achieve either an optimal T count or optimal qubits count, and that depends on your system. And for a complete overview of this quantum lookup table, you may also check out the work Unified Architecture for Quantum Lookup Tables. And next, Diyi will talk about how we actually construct the Oracle OA and OC and how to put them together.
Yeah, thanks, Shuchen, for the introduction part. So now we're ready to talk about how to use the select swap oracle or data lookup oracle to construct the amplitude oracle, which is the oracle we are going to use to prepare the coefficients within the Hamiltonian. And to start, we always first use the data lookup oracle to load the data, B0 and B1, into the quantum computer. Here, B0 indicates the sign of the coefficient. So suppose we're talking about real coefficients. And B1 is a binary representation of these coefficients. And after the data lookup, we use a sequence of Hadamard gate acting on one MB-1 qubit register, and we created a superposition state. And they will compare this I with B1. So if I is smaller than B1, we keep the last qubit in state 0. Otherwise, we keep the last qubit in state 1. And in the end, we apply another set of Hadamard gates on this I register and apply a poly Z on B0. So in the end, if we look at what's the result after the post-selection, we can see there's RB there, which exactly is the coefficient we want in the Hamiltonian. And after that, we also want to uncompute B0 and B1 by using another run of data lookup. Then we actually get our coefficient in a clean way. OK, so this slide is pretty dense. So let's talk about what we are going to construct for the OC oracle, this sparsity oracle. So what we want to construct is in this red box. And it looks really complicated. It's like a tensor product of some projection with creation and action operator. And first of all, so what is J? So J here indicates a computation basis, which is represented by a binary string. And this OJPQ means for this state J, if we look at the site Q and site P, if there's no fermion occupied on the site P, and there's a fermion occupied at site Q, then this O equals 0. Otherwise, O equals 1. So by post-selecting the O equals 0 term, we're able to do the linear combination of AP dagger AQ term, which are not vanishing. So you can see even with this definition, we can see there's some state dependency within the construction of the sparsity oracle. And now the question is, how can we actually implement this sparsity oracle? There are a few different components. So first of all, we need to implement AP dagger AQ. And also, we need to implement this what we call validation qubit, this O stuff. And for the AP dagger AQ term, we can see that if we, say, take a look at this simple example, this A2 dagger A0 state 110, so it will have two influence on the state. First of all, the action of operator will create one phase, which is corresponding to the long Pauli string within the Jordan-Wigner transformation. And secondly, this AP dagger AQ will do the bit flips on the state 110 on the side 2 and 0. So now, how can we construct this phase? The first circuit on the upper left shows one way to construct the phase generated by the AP dagger AQ. And you can see that this circuit is specifically designed for the one PQ pair. And now the question is, how can we make the circuit most efficient? Otherwise, we need to have n squared such circuit to implement all the phases. And the way to do that is we exactly implement the same thing, but with much efficient oracle in the circuit under that circuit. And we can just look up the state stored on the P's and Q's qubit, and we act on a Z Pauli Z there, and then we swap back. So this is one oracle which can compute the phase for all the PQ pair. So by doing this, we can actually reduce the complexity from On squared to On. Now, how about computing the bit flip part? So the third circuit on the right-hand side, the top one, actually shows how to compute the O and how to do the bit flip part for the AP dagger AQ. A short message is we simply use a CNOT gate to do the bit flip, and we do use the swap up gate to look up data stored in P and Q spot, and then we decide whether this AP dagger AQ is a vanishing term or not. So in the end, we can take a look at a very simple example, which is we just look at the number operator where there's no phase and there's no bit flips. The only thing we need to decide is this a valid computation or not? So for the state J, is AP dagger AQ equals 0 or not? The way to decide this is we simply use a swap-up gate, which is indicated by the SW, and we look at what data is stored in JP. And if this is 1, that means AP dagger AP is non-vanishing. Otherwise, it is vanishing. This is the construction of the sparsity oracle, and we can actually do the linear combination of the number operator and the general one-body term to construct a block encoding for the general one-body Hamiltonian. So you might be curious why we can achieve this speed up and reduction in the T-gate count. So here, if you look at the table within the row of general Hamiltonian, you can see that there's a free parameter lambda 1. And it is a parameter ranging from 1 to n to the power of 4. And by doing a simple calculation, you can see that we can find the optimal lambda 1, which achieves the optimal T count. However, when we're choosing this optimal lambda, we can see that the number of qubits actually change from order of n to order of n squared. And also, we want to emphasize this is not, this comparison is not saying that the other methods are not good, but this is an alternative way. And if we're choosing lambda equals 1, we can find that our method have exactly same complexity compared with previous Babush paper. So this is a trade-off between T-gate and the qubits. And now, in the next step, we're going to talk about how to further improve the complexity of block encoding, taking advantage of the structure of Hamiltonian. So usually in the chemistry, material science, the Hamiltonian you're caring about have specific structure. For example, for the first one, this is a general format of the electronic structure Hamiltonian, and it commutes with a number operator. And secondly, for many Hamiltonian, there is some coefficient which is not just a rank 2 tensor, but actually it is a function of P minus Q. So this indicates some translation invariancy within the Hamiltonian structure. Thirdly, when you do the second quantization, you need to first select your basis. And usually the basis has certain decaying property, and those property will go into the coefficient within the second quantized Hamiltonian. For example, for this free fermion model, this HPQ can have exponential decay. So let me first talk about the first structure. So for the H commutes with the number operator, and one way to take advantage of this structure is when we do the simulation, we may be just curious about the simulation with respect to the eta particle state simulation. So in that case, there's no need to block encode the whole Hamiltonian, but we can only block encode a subspace, a smaller block within the large Hamiltonian. And what we developed here is we developed a state-dependent empty oracle. You can see here, we're not doing the superposition of, say, I equals 0 to n for this number operator, but we're only doing the superposition from I to eta minus 1. And the coefficient we log here is H address ij. And this H address ij means for the state j, we want to see what's the address of the ith fermion occupied. And that is implemented by another oracle called Occupation Detection Oracle, OCC oracle, in another red box. So by using this address ij, we're able to firstly reduce the subtraction factor and also makes the data lookup oracle simpler. Similarly, we also want to use this address ij to develop a state-dependent sparsity oracle. So this is a simple example for the number operator. In this case, the OJ address ij is always 0 because the definition of address ij is the address for the ith fermion occupied within the state j. So this is always valid. Let me skip some detailed calculation, and let me just show a global circuit structure for the free fermion model for eta particle case. And the first blue part is state-dependent empty oracle, and the second part is state-dependent sparsity oracle. So now let's think about why can we actually get reduction for the eta particle Hamiltonian block encoding. So first of all, because the structure of the problem, we're caring about eta particle state simulation. So therefore, there are not all the coefficients are required in this computation. So that's actually directly give a reduction in the subtraction factor alpha. For the number operator case, that's exactly eta. For the eta particle state, only eta coefficient will be needed. And let's think about when we construct the epsilon precision block encoding, and if there are only eta coefficient needed, and the precision for each coefficient is only required to be at the scale of epsilon over eta. And that means the binary representation of this coefficient, if we look at the length of that, the word length MB, can be reduced from scale log n over epsilon to log eta over epsilon. And similarly, for the free fermion model, we have similar reduction. And that is the key why we can reduce the complexity for the eta particle state case. You can also see that we can generalize this approach not for the free fermion model, but also for the general second quantized Hamiltonian. And we have both improvements with respect to n and epsilon for the T case. In the end, let me quickly just cover what's the idea for using other structure. This translation invariant structure, the key idea is we can use the data lookup oracle to load a rank 2 tensor with the complexity O(n) squared. However, since this format, this T is a function of P minus Q, so we can compute P minus Q on the quantum computer and then use the data lookup to load the data. And that will reduce the complexity for number of data from n squared to n. And similarly, for the decaying structure Hamiltonian, where this HPQ decay exponentially, if we want to achieve the epsilon precision block encoding, only n log n over epsilon term are required, and that will reduce the word length as well. And in the really extreme case, when the decay is really fast, so that means alpha 0 is of the scale of log 1 over epsilon, then there's no need to keep more than one term. we only need to keep HP p plus 1 and HP p minus 1. So that's a way how we use the structure to reduce the complexity for block encoding. So in the end, let me summarize what we did in this work. So first of all, we developed block encoding which reduced the T-gate count. And we developed eta particle Hamiltonian block encoding with state-dependent empty oracle and state-dependent sparsity oracle. And this is done through a technique called indirect diffusion. And the effect is we can reduce the simulation factor and reduce the T-gate counts. And furthermore, we extend this framework to the Hamiltonian with more structure, including transition invariance and some nearest hope, some like decaying coefficients. And for the future work, we're going to think about how to extend this framework to the first quantized version, and also for the second quantized Hamiltonian, many of those examples coming from initial calculation. So there might be some interesting structure, like maybe tensor structure within the this second quantized Hamiltonian, and we hope to further reduce the complexity. And thank you for your attention, and please let us know for any questions.